not projected, it's fine.
So today I would like to talk a little bit about hyperparameter optimization, because it's a point when scikit-learn can meet PySpark. So who of you use Python for data science jobs? Not that much. Okay, but it's probably for you. Even though if you don't have a very big data set, PySpark or Spark in general could be very beneficial. So even if your data set is very small, if it doesn't remain memory, you still might have a big computation problem, in which a high degree of parallelization come in handy. So I assume all of you know this kind of workflow. So you have initial question, business question, you get the data to solve this question or the problem, you prepare the data, you munch it, you clean it, you enter the modeling phase where you try to solve a regression problem or a classification problem. And during this step, you need to tune parameters for your models. After that, you evaluate them. If they're good enough, you go to deployment. If you say there's data missing, you glitch, you go back to scratch and cycle again and again. So during this step, as I mentioned, you need to tune the knobs of the model. So the model can have an arbitrary amount of knobs depending on the implementation and the type of the model. And each knob may influence certain factors, which in the sum, they contribute to the overall accuracy or measure of your demand. So for example, some knobs may influence the robustness of the model, some the complexity, and some may help with class imbalance problems, for example. So what is hyperparameter optimization? It's the task or the problem of choosing a set of parameters for a learning algorithm in order to avoid overfitting and with respect to certain measures of optimality or quality. So there are several approaches, like grid search, random search, Bayesian optimization, but for the sake of the short talk here, I will concentrate on the grid search. So grid search is something very trivial to do. It's also done in the real world. So in this small picture example, we have a two-dimensional space. So who of you do know the character Sheldon Cooper from Big Bang Theory? Come on, not more? Okay, so those of you know that Sheldon has a lot of measures of quality where to sit in the living room. So if you go to this living room, you see, okay, Sheldon most likely would avoid certain spaces near to the corners because he cannot see the TV. Sheldon would avoid the window, the left bottom, because it's too cold there. So grid search works best if you have some intuition about the data, about the problem, and so you can cut down the search space because the task itself is already embarrassingly parallelizable, so you don't have to make it worse. But Sheldon would then say, okay, the couch error is good, and he tried different spots, so that at the end, yeah, he finds a sweet spot where he can sit, similar to like our model, finds a sweet spot with respect to certain measures of quality. So now it gets a little bit technical. Assuming we have some data, I have generated for my experiments a few data with scikit-learn. Now we have a classification problem, and I built a random forest model with the default parameters. So the data might not necessarily be really big, so I tried with 10 megabyte, 15 megabyte, 100 megabyte, a gigabyte. It's still not a big data problem, right? But you have a lot of knobs. So I trained it with the random forest classifier with the default parameters. And I get accuracy for a 5-class classification problem of 0.99, which is quite good, you will imagine. But, well, it does not, because it's overfitted, it not generalizes, and the test score is just awful. I think in a binary test it will be even worse than random guess, but it's a 5-class problem, so it's better than random guess. Yes, again, it's overfitted. So what do? We go back to our model and tune those knobs. So this implementation of random forest from scikit-learn has those knobs, and we need to tune them in order to improve the scores. So what do? I took for my experiments 2 parameters, the number of estimators and the max depth of the decision trees in the ensemble. And now you can apply some intuition or some knowledge we have from other experiments. For example, I know that an ensemble of size of 10 was not the cleverest idea. I need much more, so I take from 100 to 200. Then I know that each decision tree in the ensemble, for example, if I have a lot of columns, then a size of 4 for the depth is not enough to train all the patterns, or see all the patterns, and remember them. So I cut away 1 to 4, and I also know if I choose 2 deep trees, they will overfit, because they then will get rigid to the patterns. So I cut on the right side also. What we now do is we import from scikit-learn the grid search module and put in the random forest classifier, the default one, and gives the parameters for tune, sets the cross-validation to 3, and just hit the job. And we end up with, I hope you can see it in the back rows, for, I mean, this is around 180 different candidates. With a cross-validation of 3, we end up with over 500 jobs, which means in a single core setup, like if you have 1 core, you would have to wait 30 minutes. If you have more cores, you would wait less. But still, on a local setup, you are limited maybe to 8, 16 threads. And if the data gets bigger, and imagine I only took a small, very small grid. If I take all parameters and expand the grid, make it finer, you end up basically with 50,000, 60,000 possible jobs you have to run. And you don't want to wait 5 hours for your parameters. So when does Spark come into play? I mean, it's a trivial task for parallelization. So, yes. Of course, it's worth the effort, because after the grid search, you can return the best model. It's this, you see with max depth of 15, and the number of estimates is 200, and you see the improvement of accuracy from 0.44 to 0.67, which is an improvement, still not perfect, but it's a starting point. So, there's a package called Spark scikit-learn, and it gives you also the possibility to import a grid search module with nearly the same API than that from scikit-learn. So I have the same data. I built the random forest classifier with default parameters, put it into the grid search, hand over the Spark context. So when you have the Spark context available in your notebook, you hand it over. Then you run the job, and with the same amount of jobs you have to run, you get the result in 28 seconds. Of course, those are now small numbers, 30 minutes, 28 seconds. But imagine we have 50,000 jobs, which would be the night. You have to wait for it. But if you have for a small amount of time a Spark cluster, you can more interactively work in your flow and get those results and just concentrate on more important problems. So for those of you who are on Kaggle, for example, there are forums where they share the parameters because it just takes time to find them. And if you build an ensemble, then you have like, if you have an ensemble of 3, then you'd have to train those and the hyperparameters of the ensemble again. So with every model you add, you blow up the complexity and more jobs to run. So, but what do you get? You save time. So as you can see, the amount of time will reduce. Not necessarily linearly, because on Spark we have overhead, but you will save time. And this time you save, you can concentrate on more important tasks during your data science workflow, which means concentrating on the actual fun parts like feature engineering or selecting different models, answer the actual business question, so you can cycle faster. So for example, when I was a student, I remember I had some gig of data, I trained them, I know, okay, now comes cross-validation, I put this task to maybe 8 in the evening, so I know that at 2 in the morning I could have a peak, because I know it will take 5 to 6 hours, but if it only takes 15 minutes or 30 minutes, you can work more interactively or iteratively faster. So there's a PyPy package called, you can install easily. And I have 1 minute. Okay, and I also run my experiments on our cloud platform, DSX. I set it up, so it's installable there. I have access to a Spark cluster with a high degree of parallelization. So I invite you who might be interested in this task to join me later and just run a few experiments. Thank you.
Excellent work.